So this QOD video is relatively short presentation. So in honor of our departed but still much beloved classmate Russell, I'm going to start by showing you this video that he sent me, and this will take about 3 minutes. Okay, so two things about that video. Sorry. So two things about that video. One was that the guy on the far left was like the spitting image of Jon Stewart. And then there was that other guy in the middle who basically had like 2 moments of glory and spent the rest of the time with this kind of spaced out look on his face, sort of like Kirkman. All right, so what is the subject of our QOD video presentation this time? Well, we're talking about gases. So let's talk about ideal gases. And the question is, what actually is an ideal gas? And the answer to the question of what an ideal gas is a gas that obeys the ideal gas equation. And so the reality of all this is that there is in fact no gas that is an entirely ideal gas. And so we can really just think about gases and classify them as being ideal to the extent that they obey the ideal gas equation, which for some gases they conform to it more closely than others. And so you may remember this from your textbook. I just took a picture of this and stuck it in here. Here is So if you have 1 mole of a gas at STP, an ideal gas is going to occupy 22.41 liters. And then this is data for a series of real gases: chlorine, carbon dioxide, ammonia, nitrogen, helium, and hydrogen. You can see that they all, particularly these 4 over here, at this temperature and pressure conform fairly closely to the ideal gas law. And it falls off a little bit over here. But in a second, we're going to see that even gases like nitrogen and hydrogen do behave in non-ideal ways under more extreme conditions. So the bottom line is that no real gases are ideal gases. They're all going to deviate from the ideal gas law to some extent. And a simple way to think about this is just to say one of the empirical gas laws that falls out of the ideal gas law is Charles' law. And if you'll recall, Charles' law says that volume is proportional to temperature. That is, volume is equal to temperature times a constant. And the sort of logical extension of this is that if this was true at all temperatures, then we could actually reduce the volume of a gas to having no volume by lowering the temperature to 0 kelvins. In other words, if volume is directly proportional to temperature, then if we can make temperature equal to 0, volume would be equal to 0. Well, of course, that can't possibly happen. Any gas, if we lower its temperature enough, first of all, it's going to condense into a liquid. And then because that liquid consists of molecules that have real volume, it's impossible to get the volume of a gas down to 0. And so that's just kind of a simple example of an instance in which I can sort of prove to you in a way that's sort of intuitively obvious that no gas behaves ideally under all circumstances. So real gases are going to deviate from ideal behavior, and they're going to deviate from ideal behavior for a couple of reasons. The first thing is that contrary to one of the tenets of the kinetic molecular theory, gas molecules actually do have actual volumes, and I was just talking about that when it comes to condensing it down into a liquid. You can't make those molecules go away. They're not just points in space. They actually do have volume. So you can't reduce the volume of a gas to 0. So one of the tenets of the kinetic molecular theory is that the volume of the molecules is so small relative to the volume that the gas occupies that the volume of the molecules can be considered negligible. But that's not actually true. They do have volume. And the other thing is that contrary to one of the sort of tenets of the kinetic molecular theory, there are actually attractive forces between gas molecules. Now, at sort of standard temperatures and pressures, they are more or less negligible, but as you lower the temperature, those attractive forces actually become more significant as the kinetic energy of the molecules decreases, and that's actually what causes a gas to condense into a liquid. The fact that those attractive forces become significant to the point that they actually begin to assert themselves. So when do real gases behave ideally, and when do real gases tend to not behave ideally? Real gases are going to tend to behave ideally at low pressures. And that's because as you decrease the pressure, and if you think about this, how are you going to decrease the pressure of a gas? Simplest way to do that is just by increasing the volume of the container that it's in. As you decrease the pressure, that means that the distance between molecules is increasing, and therefore the volumes of the individual molecules do become less significant. So at the lower pressures, you are more closely approximating that tenet of the kinetic molecular theory that the volumes of the gas molecules themselves are negligible. Similarly, at high temperatures, if you increase the temperature of a gas, then its kinetic energy, the kinetic energy of those, and therefore the speed of those molecules is going to increase, and that will really overcome any tendency they have to exhibit attractive forces toward each other. So as temperature increases, those attractive forces become less significant and again begin to approximate the kinetic molecular theory, which says that attractive forces are negligible. So here are some pictures from your textbook, and I'm not going to go over in great detail what the significance of them is, but if you look at these various gases, and we've got nitrogen, methane, hydrogen, and carbon dioxide, you'll see they're behaving very ideally. So what is this? You take 1 mole of a gas and you have it at you take 1 mole of a gas and you have it at some fixed volume at standard temperature, and you start to crank up the pressure of that gas really high, and then you look to see whether PV over RT is equal to 1, because if you got 1 mole, if it's behaving ideally, then PV over RT should be equal to 1. And you'll see that at relatively low pressures, that is at pressures between 0 and 1 atmosphere, they behave very ideally. But as the pressure starts to go up, they start to deviate significantly from ideal pressure. I'm not going to talk in detail about why it goes down before it goes up, but you'll see that particularly in the case of methane and carbon dioxide, you get this big swing, but eventually everything starts occupying more volume than a real gas would occupy, and that's why these lines go up here above the line of 1. And there's also a temperature dependence to this. This is nitrogen gas, and you can see, depending on what the temperature is, 200 kelvins, which is well below freezing point of water, 500 kelvins, 1,000 kelvins, affects how it behaves. Once more, we said that at higher temperatures, gases behave more ideally, and you can see actually that nitrogen is behaving more ideally as the temperature goes up. So this is just a sort of pictorial graphic to indicate what I was saying before. At low pressures, the distance between the molecules is relatively large, and so their individual volumes become more negligible relative to the volume of the container. At higher pressures, they're closer together, and so their individual volumes are more significant relative to the volume of the container. At high temperatures, these atoms, molecules, are moving very fast relative to each other, and so attractions between particles are pretty much insignificant, and so the force of a particle striking the surface of the container is going to be greater. As we cool a gas down, now a real gas, these attractive forces between particles start to become more significant, and that is going to tend to decrease the force with which a particle, a molecule, an atom strikes the surface of the container. Okay, well, how can we actually account quantitatively for the real behavior of gases? Well, we can do that by taking the ideal gas equation and using some extra bits, adding some extra bits to it that take into account the behavior of real gases, and this corrected equation is known as the van der Waals equation. So here is what the van der Waals equation actually looks like. The nRT side remains constant, but we have these corrections, and so the pressure is corrected based on a constant called A, and that constant varies depending on what the substance is we're talking about. And we also have to correct for the volume, and that volume is going to be corrected for using a constant called B, which again varies depending on what the gas is. Essentially, A corrects for attractive forces between molecules, and so that is going to tend to make the pressure lower. And B corrects for the size of the molecule. And so this is an equation that I may put an example on the test of this. It's a very simple thing to do. You'll be given a volume, and you'll be given a number of moles, and you'll be given a temperature, and you'll simply be asked to say, okay, say, for example, calculate what the pressure of that gas would be if it were an ideal gas, and now substitute in the constants for whatever that is and calculate what the actual pressure is going to be. And so that's a fairly straightforward calculation. The College Board may or may not, probably not, have you do that on the AP exam. But what they are interested in having you do, and what I would do on a QOD, is talk about what I talked about at the beginning of this presentation, which is explaining why it is that gases do not behave ideally, and talking about under what conditions gases would tend to behave more ideally, and under what conditions gases would tend to behave less ideally. So that's what you can expect on a QOD. And so thanks for watching.